Hi everyone, thanks for joining our talk about OpenShift in an air-gapped environment with GitOps. We will show you how GitOps made our life easier. This is a moment from the beginning of our journey. They were two different teams in one room trying to describe the elephant. They were VMware infrastructure team and DevOps team. We were drawing on the board and trying to define the project scope with no success. Nobody understood the whole process, and each team only saw its part of the picture. So what that elephant actually was? Installing a fresh OpenShift 3 cluster in an air-gapped environment. At first, we thought that this was really hard, but then we realized that this was also frustrating. My name is Regina. I'm leading cloud-native adoption in the bank and administering on-prem OpenShift environments. And since I was a child, I was always the only female somewhere. I was the only girl in class, and I'm one of the few women lecturing in DevOps areas. As you can see, I'm also outnumbered in my own family.
My name is Shereg. I'm part of the VMware team, currently working on OpenShift, previously Linux administrator, and together with Regina, we work in Hapoalim. Hapoalim is a big financial organization under strict regulation, and the risk is that on the other side of any internet connection, armed robbery rates. So every connection is a risk, but this approach comes with a cost. But let's talk first about cloud. Amazon AWS, Microsoft Azure, and Google GCD are part of what we call internally the public cloud utopia. You want to install a Kubernetes cluster or any other product? No problem. The installation is quick and easy. You can use managed service. The product comes already installed for your convenience. You can deploy multiple environments in a click of a mouse. No need to design special architectures for that. Also, the vendor can take part of the installation, and logs can be sent to the vendor for troubleshooting. Another benefit of the public cloud is that you can try before you buy. In some cases, instead of committing to the product, you can deploy and delete it and pay only for the time the deployment is up. In the cloud, we can use product as the vendor intended them to be used, without making any modifications to run them on our on-premise environment. In the cloud, we can also auto-provision preferred infrastructure, such as networking, and focus on the products that we need. Specifically, a Kubernetes cluster, and the use of third-party tools is simple with easy integration. Utopia, right? But we are not in the public cloud. We are an air-gapped environment. So we can't use all the goodies of the public cloud. As I said, we are an on-prem environment. So there are some hardships unique to this environment. We need to manually install and provision the VM to have a compute nodes. We need to manually provision networking and security, or the VMs will not talk to each other. We need to do user-managed initial storage allocation. We don't have the installation images and packages on our network. And when we manage to fix it, the install scripts fail several times. When the diluted cluster is up, we haven't ended our problems. We have to self-manage cluster resource consumption, or the cluster will not be able to run all our workloads. And God forbid talking about upgrading the live environment. It is insanely hard, and the users are allergic to any downtime windows. So the takeaway message is don't run on air-gapped environment if you can. And now that we understood that our goal is to install OpenShift cluster automatically in an air-gapped environment, and that the task is challenging, we will now move to the basics. What is on our playground? What was the foundation of the project? The basics. Our infrastructure for the project is VMware infrastructure with software-defined networking and security and NAS storage. The existing process to install a cluster had VRA auto-provisioned VMs, OpenShift manual installation, manual post-install configuration, and the management and monitoring tools such as Prometheus, Grafana, and Uncode were configured with ArgoCD. What is wrong with the existing process? Well, it had 50 steps and was a mess. It included Ansible playbooks in their own Git repo and chef cookbooks in their own Git repo. Part of the process involved Jenkins jobs, while other stuff was done with manual scripts or even manual tasks. Part of the process was done as if by voodoo magic. We had undocumented steps that needed to be done, and the deployment was successful only where those steps were taken. We had scripts on servers, we had scripts in people's minds. And since we didn't mention enough Git, we had more Git repo managed by ArgoCD. Our two teams tried to describe the elephants and put us automation steps in their own niche. But all the integration was done by a duct tape. Change was needed tremendously.
Step toward the right side. We were deeply inspired by GitOps, but no GitOps for infrastructure parts existed, not at least 2 years ago. I mean, how can you create virtual machines with VMware using GitOps? So we realized that many of the steps will be imperative. The following requirements became crystal clear for us. We're going to need a single Git repo with all the source code for all the different installation steps so that we can all look in the same place. We need a single orchestration tool to run all the steps, some of them serially and some in parallel. We will also need the ability to orchestrate steps in different technologies, Ansible, Python, Bash, and even more, because people had different skills at their everyday work, and we wanted to preserve that flexibility. The orchestration tool must have tight integration with Git, as the desired state of the different products was already in Git managed by ArgoCD. And so the automation basics, as we outlined them, were as following. We're going to use as much GitOps as possible, and we're going to do that with a central ArgoCD instance. Our cluster desired state is going to be comprised of two things: manifests and their corresponding Argo apps. Yeah, this is a key concept here, that Argo apps are also part of the state. We will use GitlabCI as the orchestrator to run all those different steps. And we're going to have everything in Git, both GitOps stuff and non-GitOps stuff. I'm going to talk about the GitOps and non-GitOps part throughout the entire session. We will also use Argo Umbrella app per cluster. This Argo Umbrella app will sync all the other apps. And so this is our main automation flows. Yeah, we're going to create the virtual machines. Then we're going to perform pre-installation tasks, install OpenShift, perform post-installation tasks, prepare the GitOps manifests, and we're going to create the Argo project, create the Argo Umbrella app and the Argo cluster secrets. Then we're going to wait for the Argo apps to sync. Then we're going to run tests. So this is the whole automation process of installing OpenShift 3. There are 6 main parts here. The IS pre part is creating the virtual machines and is preparing them for OpenShift. The IS install part is the part that actually runs the Ansible playbook that is installing OpenShift. And the IS post-installation part is the part that performs post-installation configuration of OpenShift. Now the platform part. The platform pre-install part is preparing the cluster to be managed by ArgoCD. And it is also installing and configuring products that need imperative steps in them. The platform install part is preparing Argo apps for the new cluster. And also the actual kubectl apply on the project, on the umbrella app happens here. And then the automation process waits for the important Argo apps to sync, and afterwards it performs sanity tests on the cluster to make sure that everything was installed and configured correctly. This is how the desired state of an OCP cluster looks like. I cannot show you the exact products that we're using, but the important thing to understand is that for each product that you see on the left side, there is a corresponding Argo app managing its state. Let's take the outcode collector as an example to explain how we manage the cluster product configuration with GitOps. The following Argo app manifest is part of the desired state. The manifest will be different among the different clusters, so it is templated. The cluster name and the cluster URL are different. The automation will process this template and inject cluster-specific data in here. This is an example of a templated product manifest with cluster-specific configuration. I'm sticking to the outcode example for now. So this product, as many others, do not come as a Helm chart, so we chose Ansible templates to handle that. The cluster name, again, will be different per cluster. One of the automation steps will process these templates and commit the final manifests to the Git path, which the Argo app I showed you earlier is watching. So we have imperative automation steps that are preparing manifests for the GitOps phase and committing them to GitOps desired state location in Git. Cluster configuration is comprised of general configuration and cluster-specific configuration. And so the templates filled with cluster-specific values are the cluster final configuration. Template-based branch has the Ansible tasks for the installation and the generate plus templated GitOps manifests. It also has the template Ansible hosts for the Red Hat OpenShift installation playbook. Now, GitlabCI pipeline runs on the template-based branch. It creates a new branch that is named, for example, Dev Cluster 5 or Prod Cluster 2. And so the final configuration is in the branch, Dev Cluster 5 or Prod Cluster 2. This is a common Git flow for the feature release where the template-based branch is the main branch and people are working on feature branches to add more functionality to the automation. Each pipeline run on the main branch results with two things: a new live OpenShift cluster and a Git branch that is named after it. So the branch has both GitOps manifests and non-GitOps content. So the cluster and the branch are two inseparable entities. After integration tests are run on the created cluster, they are part of the same pipeline that builds the cluster. The feature branch is merged back into the main branch. So next time a GitlabCI pipeline would run on the template-based branch, a new cluster with the changes from the merged features will be created. At this point, the OpenShift installation automation was distributed like this: 30% of GitOps content and 70% of non-GitOps imperative tasks. The result, with one click, the cluster was up after 3 hours and it was fully functional with required namespaces and applications. And multiple such clusters can be created in parallel. We had high confidence in the created clusters because the troubleshooting here was easy. The steps are clear and they're all in a known location and everything is documented. Being deeply inspired by GitOps, we managed to glue those 50 steps together and to eliminate the steps in people's minds. In the end, we managed to tame the elephant and to perform fully automated install of OpenShift 3 cluster in an air-gapped environment. This is a GitlabCI pipeline that creates an OpenShift cluster. I like to call it a carpet. As you can see, there are around 50 steps in there. Are you familiar with the feeling of falling in love with something that you have developed? So this happened to me too. I fell in love with that automation that we did, but I realized that I have to become emotionally unattached to what we have built so that improvements could be made, and improvements were needed. I soon found out there was a constant need to introduce new products to new clusters, and those products had some imperative logic to be performed and desired state. Some of them had environment-specific configuration, while others had CTL tools to invoke, and only then their desired state could be managed. So in order to do that, other teams needed to learn about the automation process, and they needed to integrate with it. More imperative steps needed to be added to the long pipeline we already had. It was time-consuming, and we started to look for a way to enable independent contributions. So we did a redesign. By the new design, the installation of the new product will be done by an Ansible operator running in the cluster instead of a step in the GitlabCI pipeline. The product will be treated as a plugin. And so clusters can have different plugins without being dependent on the GitlabCI steps that created the cluster. Kind of Lego building blocks. Now, the product contributor, the person who wants to install this product on the cluster, will provide the relevant Ansible role for the imperative logic and will also provide the manifests with the desired state Git location. The operator will import the provided pre-install Ansible role for the product. Yeah, the role is in Git. Then it will create an Argo app to watch the desired state location that was also provided. And if some post-install logic is needed, then it can import and run it as well. Again, the post-install Ansible role will be provided by the person contributing this product to the automation. So sticking to the same outcode example, now instead of an imperative Ansible step in the automation, there is a custom resource that tells the operator to perform the same logic. This custom resource is declarative, so ArgoCD can manage it. That means less non-GitOps steps and more GitOps content. The Ansible operator was developed with Operator SDK and had different config per cluster, so I used customized overlays for that. For each new cluster, a new overlay had to be created. So I kind of hit the chicken and egg problem. Now, how can I install this operator easily on a new cluster in an automatic way? That introduced another complexity, and so the ROI became too low. I will change the release cycle of the operator in the future. Lately, I discovered that there is a GitOps part in Red Hat Advanced Cluster Management. Red Hat Advanced Cluster Management prehook steps can be also implemented as Ansible role, but they require Ansible Tower to run them. So it looks like Red Hat is also investing in solutions that combine GitOps and non-GitOps worlds, but with a different design. Another problem. Let's say that I've installed Litmus. On one of our clusters, I tested it, and I decided that each of our other clusters should also have Litmus installed. So in the current design, Litmus manifests are general. They do not have any environment-specific configuration. But they have to be duplicated among all the branches. So actually, most of the products we use have common configuration, and only about 20% are environment dependent. So the branches for the different clusters cannot be merged into each other because of the 20% that have environment-specific configuration. And the meaning is that those identical manifests have to be copied manually from branch to branch. So we did a redesign. The solution is common desired state for 80% of the cases. Now, this design is much better. The common manifests reside only in two branches, the dev desired state and the prod desired state. Yeah, so this one is for all the dev environments and this one is for all the prod environments. Now, introducing the litmus to all the dev environments is as easy as committing once to the common branch. The ArgoCD of litmus are still different per cluster, so they remain in the original branch. And if we take the outcode manifest that I've mentioned earlier, they are also cluster specific, so they also remain in the original branch. But now what happened is that I can take those general common manifests from dev desired state branch, and now I can auto-merge them. I can automatically merge them into the prod desired state cluster. And I do not need to copy them over manually. Another problem that we had was long integration time for new features. When adding a new feature to the automation, a new cluster has to be created successfully, and all its tests must pass before the feature can be merged back into the main branch. But the cluster creation can fail before reaching the step that introduces a new feature. That can happen if we run out of resources on the infrastructure side, or because some network error occurred. And so reaching the new step can sometimes lead to a very long integration time. In this example, I waited for 2 hours just to fail. So this is an example of new steps that were not reached. Yeah, the new steps were here, and a long rerun is needed. So we did a redesign. We decided to separate the IaaS and the platform into 2 different repos and into 2 different pipelines. As a bonus, we realized that when we moved to public cloud, the IaaS part will be completely different and we will be able to replace it easily. And then OpenShift 4 came out. So OpenShift 4 is an evolution and a revolution altogether. OpenShift is declarative to the bone. It's clearly GitOps inspired. Everything is an operator. Monitoring stack configuration is now declarative. It means no more running Ansible playbooks to configure alert manager receivers. OpenShift 4 configuration itself is declarative. It means that no more editing the master conf is needed. There is an operator for auth configuration. There is an operator for ingress controller configurations and many more. Even operating system level configuration is declarative. We can use the machine config CR, for example, to configure cronny. And what happened as a result is that the non-GitOps part in our automation shrunk significantly. Now, most of the automation is declarative and managed with desired state. The more GitOps desired state we have, the more flexibility and control we gain. So we kind of flipped around. Now the majority is GitOps. Remember the long GitlabCI YAML from OpenShift 3 installation? With OpenShift 4, the IaaS non-GitOps part is extremely short and simple. That's it. It used to be very long. As for the GitOps part growth, with OpenShift 3, we had about 17 Argo apps. With OpenShift 4, we doubled that amount. So all of those are the new Argo apps that we're using. I can only show you some of those. The growth in the desired state that we managed came both from operator hub operators that can be easily installed in OpenShift 4 and from the configuration steps that were previously imperative and done with Ansible, and now they are declarative and can be managed with GitOps. The number of the steps and the installation duration drastically reduced. Now it's very short. Because of collaborative nature of GitOps, we can tackle bigger projects, especially in pandemic times. GitOps is bringing people together. So another cultural changes that we've seen is that at the beginning, people were implementing tasks in their comfort zone. And as the project evolved, we all started taking tasks outside of our comfort zone and out of our professional silo and solved problems across the entire project. The learning and the knowledge sharing was enormous. Before we started the project, the environment changes were undocumented, and with GitOps, every change is documented, tested, and tracked, so accountability improved drastically. To conclude, do you remember the air-gapped hell I showed you earlier? With GitOps inspiration, it turned to a cozy place to be. We would love to hear from you. You can reach us by LinkedIn. I want to say thanks to our teams. We could not have done this without you, and huge special thanks to Sheleg. And thank you so much for watching our session.